Okay, everyone, we are back. Welcome again to our CSEC Chemistry Marathon. Right now, we are going to start our session on qualitative analysis, right? So to those of you that were not here, well, I just saying that for to be a professional. Those of you that were not here, we looked at the exam format and reviewed the stuff. So in case you missed on the recording, you can just scroll back a little earlier to take a look at that. Okay, so we are going to start the qualitative analysis again, as I mentioned, because it is a topic that is very important. It's a topic that is heavily assessed, and therefore we will have to look at that topic. The reason why we're starting with it is because most of you would have ended with it, and the problem with that is essentially we have rushed a very critical topic. So we need to explore a little more qualitative analysis. We need to understand a little more what it is, and we need to understand the test a little more, because we need to understand the reasons why, we need to understand the inferences why. So we are going to begin with that. Okay, so qualitative analysis is what we are looking at right now. You all should all be able to see my screen as far as I'm aware. Great. So our objectives are to identify the cations and ions present in a salt and to test for the presence of gases. All right, so that is why we do QA. I will share the slides again if you all are able to do some past paper questions on that. So salts, okay? So what is a salt, okay? So remember when we did acids and bases reaction, we realized that an acid is neutralized, we replace that hydrogen, right? So the hydrogen ion is lost and is replaced by a positive cation, whether it be from an alkali, a base, a carbonate, or a metal, right? So whatever positive ion was in that compound or in that element, it replaces the hydrogen of the acid, and voila, we form a salt. So a common example is the reaction to form sodium chloride. So we have hydrogen, chloride, hydrochloric acid, and we have sodium hydroxide. So acid and base, and we'll form the salt is sodium chloride salt and water. Okay, so one of the most common acid-base reactions. So the common salts would be copper sulfate, would be calcium chloride, would be sodium, chloride, would be ammonium bromide, zinc chloride. You could think of all of the lot of the salts, talk about different salts as well. But that's what it is. And this is important because in a salt, we'll be testing for that positive cation that is there right now. Should probably do that. Okay. So ionization of salts in water, right? We're going to talk about ionizing salts in water. So when we add a given salt in water, it readily will form an ion for us, okay? So sodium chloride, if we put it back in water, and that's what happens if you leave the salt too long, right? That is what we refer to when we want to get a dry sample of the salt, because if we leave the salt in the solution that is formed for too long, essentially this is what will happen, will form an electrolyte to form the ions, right? So we'll form the sodium ions and the chloride ions in solution. And this would be the ionization reaction and will be used for the qualitative analysis of a given salt. So that is why our samples need to be in aqueous form, so we can actually do the QA. So we need to convert it to an aqueous form or have our solution in an aqueous form. So what is qualitative analysis, right? It is the analysis, that is the detection and identification of cations and anions present in a given compound or salt mixture based on physical and chemical properties, okay? So essentially, we are deducing the identity of an unknown ionic compound. In other words, QA will not work for covalent compounds. We are talking about ions, the presence of ions, okay? So we're looking at things that would have ionic components to them, okay? Now, this ionic could be simple molecules as you're accustomed to, when you bond with maybe monatomic or polyatomic anions, cations, or they could be complex formula, complex structures, which we usually talk about when you know transition metals, etc. But we're talking about the normal type right now, okay? So we're talking about the normal type of metals right now. Okay. So for organic compounds, we refer to the organic chemistry section because most of the tests would be distinguishing tests between our alkanes, alkenes, alcohols, etc. That is how we would determine the identity of these carbons. But in terms of ionic compounds, this is the way we have to go. So we're going to start with cations, right? So performing qualitative analysis in cations. So as you expect in chemistry, it's a science, and science is involved in trial and error. And many times when we find something is true, we want to confirm that it's true. So we will do preliminary tests and we'll do confirmatory tests. Now, this is for cations specifically, because whereas several of them have a similar reaction with the solutions that we use to test for them. So one test we can formulate a hypothesis, eliminate other options, and the other test we need to confirm or disprove that and arrive at the true answer, the truth, okay? In some cases, we might have to do even more than these, as in the case with aluminum and lead ions, which we will talk about in a while. So the first test we do is with sodium hydroxide, NaOH, and then the next one with aqueous ammonia. So essentially what happens is that sodium hydroxide would react, literally would react with these metal cations to form either salts, and then ammonia now would either cause these salts to precipitate or cause these salts to disappear, depending on whether they're soluble or insoluble. So how do we use sodium hydroxide? So convention is we're going to pour the unknown salt solution into a test tube. We're going to add 3 drops of sodium hydroxide to the solution, shake the mixture, and we're going to record the observations, right? So this is where usually CSEC starts us off. So any precipitate, call of precipitate forms. And if there is a precipitate, you're going to add excess sodium hydroxide to about half the test tube full, shake the mixture, and then you're going to record the observation again. Is the precipitate soluble in excess? And that's what you would have, okay? So that's the process essentially. And these observations are usually what we get for the exam. And we're going to do the same thing with ammonia now, the exact same procedure, add 3 drops of ammonia, record observations, put in excess, and egg restorations. Now, the reactions with these metals, with sodium hydroxide, we have a general equation and we have each individual equation. So the general equation should help us remember, it's the only metal equation for qualitative analysis. So we have the M being the metal with a charge, a positive charge, whatever the positive charge is, plus the same N with the hydroxide negative. So the reason why it's N is because you will have any number of positive charges. And because each individual hydroxide ion has a charge of 1 minus. So let's say if the thing is calcium, right? Calcium has a 2+ charge, so you need 2 of the hydroxide. So that is why you'll have the same N on both sides here. And then the solution or the precipitate that you'll form, you will have the metal hydroxide being formed, okay? So it's like calcium from calcium hydroxide, aluminum hydroxide, zinc hydroxide, lead hydroxide, iron hydroxide, copper hydroxide. And we put the colors there just so you see For ammonia, you will not get any precipitates when you form ammonium hydroxide. Instead, you'll get ammonia gas let off, and we can use the litmus paper test for that. Now, all salts here will be insoluble except those of the alkali metals, just because you have a single plus with a single minus charge. So that is why they'll be soluble. So lithium hydroxide will be soluble, sodium hydroxide will be soluble, and potassium hydroxide will be soluble. Everything else would be insoluble. In terms of ammonium ions, as we mentioned before, warming with dilute sodium hydroxide solution releases ammonia gas. And this is an alkaline gas, so or a basic gas. So it of course would have a reaction with red litmus paper, turning it blue. And you also smell something like urine if you have it evolved, okay? So this is a reaction, as I mentioned before. You would have the sodium ammonium hydroxide forming essentially to effectively give you ammonia and water, okay? And this is how you would test for it. So if it is present, it's gonna turn the litmus paper blue. Now, these are the tests we need to concern ourselves with, more or less. The cations and the anions, right? And I want to introduce you to ZAP very early because these three are very, very troublesome. Zinc, aluminum, and lead. They have almost identical reactions for all three of the tests, okay? So aluminum in sodium hydroxide will give a white precipitate, and it will be soluble in excess to give color solution. The same is true for both lead and zinc. And calcium at the start. Calcium will be insoluble in excess. So if we can still see that color then we can obviously say it's calcium, that's fine. But in terms of the sodium hydroxide, aluminum, lead, and zinc, we will all have the same reaction. So that's why we have to go to the second test, being the ammonia test. So the white precipitates would remain insoluble in excess for aluminum. It would remain insoluble in excess for lead. And for zinc now, it will be soluble in excess to give a colorless solution. So we can eliminate zinc on the second test. So we'll talk a little about how we will determine the difference between aluminum and lead very soon. Calcium does not form precipitates under these conditions. Its solution is not going to change, it's going to remain colorless. So calcium can be, out of the white precipitates, calcium is the one that is easily discovered, the one that is easiest to find. So that is why ZAP, as I mentioned before, is the troublesome one, because you have these three ions essentially giving similar tests. You can eliminate zinc at the end, yes. However, aluminum and lead, we'll have to come back to that in just a moment time. Copper is the easiest one because copper, from the time you see it, you should already see the color, which is blue. It's very distinctive color, it's blue. And you notice that in sodium hydroxide, it will be insoluble in excess. In ammonia, it will turn to give a dark blue solution. So it's easy to determine copper just based on that characteristic blue color, and of course the formation of a copper hydroxide solution. Iron 2 plus.
Your message to Twin said
iron 2 plus and iron 3 plus. Iron 2 plus and iron 3 plus. Now these are the ones you have to be careful with. You may not always get to see the color at the start, right? So iron 2 solutions tend to be a little colorless. Iron 3 tend to have a little hint of orange, reddish brown about them. But we just don't know to be sure, so we still have to do the distinguishing tests for them. So iron 2 and iron 3 can be easy, right? So you did the green precipitates at the start for iron 2, and red-brown precipitate at the start for iron 3. So that would already give you the idea. Now, a source of error that can form now is if you don't do the reaction quickly enough. Because on the bottom, you'll see that the iron 2 quickly oxidizes to turn into an iron 3. Therefore, you have to watch for the first color you observe. If it oxidizes, and if they tell you it oxidizes in the exam, then you have to remember it's iron 2, because iron 3 is not going to oxidize to anything. So that will be the test between them. So by far the easiest is copper, because copper is one color all by itself. But we have to be very careful when you're doing these reactions. So just a summary, a flowchart summary. For the salt solutions, ammonia will form no precipitate, so it's another easy one to determine. White precipitates will be formed by those that are soluble, being ZAP, zinc, aluminum, and lead, and calcium will be insoluble. So calcium, we will see that insoluble precipitate forms. A colored precipitate will be given, of course, the light blue, of course, would be given for copper as expected. For iron, a dirty green precipitate for iron 2, and a brown precipitate for iron 3. But remember, these two can switch themselves. So please, I mean, you're not doing this as a lab right now, but just be guided that the two of them have similar characteristics if they are left to oxidize. All right. And for ammonia, the results are pretty much the same, not much changes. We can rule out calcium here as well. White precipitate, we can rule out zinc because it's soluble. Aluminum and lead will still be insoluble. Copper will still remain blue. Iron will still be dirty green, and iron will still be its characteristic colors for either iron 2 or iron 3 because it will not form a soluble salt. So it's very easy to confirm these three here based on the ammonia test. But now the issue is having to determine between aluminum and lead, which you're gonna come to. So aluminum and lead, they give similar results for both the tests, and we have to find a way to distinguish them. So there are two options we have. I present to you the first option, which is the easier one to remember, to use potassium iodide or any iodide containing salt. So anything that contains iodide, right? An iodide ion. Aluminum will not produce a precipitate. Aluminum will not react with iodine, okay? So aluminum doesn't react with any of the group 7 elements after bromine. So it will not produce a precipitate with iodide. And lead, however, will produce a bright yellow precipitate of lead 2 iodide. So to distinguish between the aluminum and the lead ions, we will use potassium iodide, okay? The second option we have is to use any solution containing a chloride ion or a sulfate ion. And if we remember this table, we should remember in terms of formation of salts, which salts are soluble, which salts are insoluble. We remember which salts that are soluble and insoluble. And here under chlorides and sulfates, it should tell you that all chlorides are soluble except lead 2 chloride. And the same way, all sulfates are soluble except lead 2 sulfates. So if you form a lead species with these, you get a white precipitate because it's insoluble. But if it's aluminum, it will be no precipitate because aluminum will have a soluble solution. Okay, it will form a soluble salt. So that's it for our cations. Now we go to our anions. And for the anions, it's a bit different because we differentiate based on the formation of a precipitate and the formation of a gas. Anions don't really have any confirmatory test, more say. You more or less rule out tests. The only confirmatory tests you usually have are between like species, so like halides, or between sulfite and sulfate. or between nitrite and nitrate, something like that. Okay. So we're testing for carbonate first, because carbonate ions are by the first the easiest ones to test for, just because of the fact that carbonates can be used, the same test we use for carbon dioxide can be used. We can add a dilute acid, of course, causing it to turn into carbon dioxide. So that reaction will cause carbon dioxide to be formed, and in the carbon dioxide gas in that test tube, we can bubble it through lime water, which will turn that lime water milky if we have carbonate present. So it is the easiest test to do. Just add an acid, cause it to react, and then we have bubbling the carbon dioxide gas into that. So it is a very, 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 very easy one for us. And then sulfates now. Sulfate, the test is we either add barium chloride or barium nitrate. Now, barium chloride gives better results. So barium chloride acidified with hydrochloric acid, and a white precipitate shows a positive result of the presence of a sulfate or the SO4 2- group. Okay, so barium chloride plus a sulfate would form barium sulfate, bring that white precipitate, and the chlorine ions would be dissolved out of solution. Okay, so it would be dissolved out of solution. Now, the sulfites we expect to form a precipitate that dissolves when heated to produce sulfur dioxide gas. So if we want to test, which we usually do, we usually heat this up, right? So if we heat that up and there is sulfate, then nothing will change. If we heat that up and it is a sulfite or the SO3 group, then it will dissolve and release a gas. So that is important for the test between the two of them. Yeah. So that's another test you can do for sulfites. We can use an oxidation reaction test, because if you notice, sulfur dioxide is a very strong reducing agent. So it can reduce the potassium manganate, which is what accounts for that purple color being turned onto a white or colorless. Okay, so it will reduce it. So that's another option we can have. But the first one is by far the safest option, because it's linked to the first type. So we can just put that, after we have done the solution, we can just heat it up. And if we heat it up and it disappears in the sulfite, and that's the end of the story. Now the halides, the chlorine, bromine, and iodine. These can be some tricky tests to do. So let's look at them. All right, so the first step we're going to use silver nitrate, okay? Silver nitrate should be familiar to us. Silver nitrate is used in photographic film. Silver nitrate is a solution. It's a very silver gray solution. So we're going to put silver nitrate dropwise, add it dropwise, after we add nitric acid. And the reason why we add the nitric acid is because we need to get those halides, of course, the ions dissociated, okay? So they have dissociated, and we add silver nitrate solution, okay? So at the first, all the solutions will look colorless. But then when we add the silver nitrate solution to that, we get a white precipitate of silver chloride, a cream precipitate of silver bromide, and a yellow precipitate of silver iodide. And we can base it based on the white, the cream, and the yellow. Sometimes the colors are not as evident as that, but because it is an exam, a written exam, they will tell you what color you're getting, whether it's white, cream, or yellow, or they will ask you what color you expect to get. So there shouldn't be any room for error involved in that question here, okay? And to confirm, we can also use a dilute ammonia solution. and the white precipitate of silver chloride would be soluble. So we expect it to disappear. Well, it's white already, so it's not going to disappear. Cream precipitate of silver bromide will remain insoluble, and yellow precipitate of silver will remain insoluble. So this would allow us to confirm the presence of these. Okay. Concentrated ammonia, the cream precipitate of silver bromide would dissolve. But once we have the colors already, we don't really have to go through this step again. Okay. So the nitric acid again removes the carbonate, preventing precipitate, of course, because carbon dioxide would obviously want to enter into that ionic compound. Silver nitrate would form the halide precipitate. The ammonia is to dissolve that chloride precipitate, as we can see here, and the concentrated ammonia will dissolve the bromide precipitate. So these are the tests. So if you can differentiate them on the colors, then you can use the other tests to get them out. And this is just another way we get to that. Now, after we add the concentrated ammonia, we could put them in sunlight, okay? Because the halides react differently with sunlight, right? So chlorine would turn purple gray, bromine would turn creamy gray, and iodine remain yellow. So if you have yellow all throughout, then it would remain as an iodide solution. All the others, of course, would change their state. But these are the tests that we can know. So, I mean, we could really stop here. Well, if we want, to go further down this direction. And now we're testing for the nitrates, so the NO3 minus ions, right? So we're gonna add a few drops of sodium hydroxide. We're gonna add some aluminum powder, essentially. So this is what we do. We're gonna heat it up. And then this will produce the ammonium ions, which break down to form ammonia, okay? And then we test with red litmus paper or blue. So essentially, confirming the test for nitrates is essentially forcing it to form ammonia and then testing for the ammonia. That's just because in the presence of a metal, in the presence of the hydroxide under heat, we're gonna get that to form ammonium hydroxide. And that will be converted back to ammonia like we saw in the reaction earlier on, right? So this we don't need to know, but it results in forming the gas. So an anion summary, just to look at it, okay? Carbonate, of course, CO2 liberated by dilute acids, that's simple. Chlorine gives white precipitate with silver, gives white precipitate with lead. Bromine gives cream precipitate with silver. So silver chloride is the one we should use. Iodide gives yellow precipitate with the silver, insoluble in the ammonia. Nitrate, of course, we know the ammonia will be liberated on heating with a hydroxide and aluminum foil. Sulfate, we give a white precipitate with barium chloride. Now, we have lead here because we used to use lead before, but because of safety reasons, we no longer use the lead in the lab. So it used to be lead chloride that was the reagent going around, but because of health reasons, we no longer use lead. So that's that. If you put lead on the exam, then you shouldn't get it wrong, but I mean, it might cause a little question. So let's stay with the new agenda in getting that to go. Okay. Sulfate, of course, gives white precipitate to barium. Sulfite, you would notice that it would reduce manganate, or you could just heat up the solution formed above. And if it disappears, then that shows sulfite. So last thing we need to know if QA is testing for gases. So some gases we have to test for, okay? So ammonia, again, we've seen how we test for that. Ammonia is a basic gas, so it should turn red litmus paper blue. And chlorine is an acidic gas, so it should turn blue litmus paper red before it bleaches it to white. Now, of course, you go to them solely on their smells. Of course, one having a choking smell, the other one smelling like urine. That's another one for on terms of observations. Oxygen, that it would be the splint test. Oxygen will relight a glowing splint. And hydrogen will cause a splint to pop. Okay, so you hear that big pop sound when you use hydrogen. Carbon dioxide, as we spoke before, we bubble it through lime water, forming calcium carbonate. And sulfur dioxide will bubble sulfur dioxide into acidified potassium manganate. Because sulfur dioxide is a strong reducing agent, it will change the color from purple to colorless. And acidified potassium dichromate can also be used, where of course we'd see the redox reaction occurring as well. Water vapor, very nice test. It's to use blue cobalt chloride paper, and it will change to pink if water is present, okay? And this is just a summary of the tests for the gases that we have to know for qualitative analysis, okay? So do we have any questions on QA, qualitative analysis? Is there anything that we want to go over?
So I'm just so if you utilize lead, so it's best not to utilize lead in your answers, right?
Yes, yes. In some of the textbooks, you will still see lead being there because we used to use lead in the lab. But because of the dangers, of course, of lead poisoning, they've slowly stopped using lead. So that is why in most of the if I go back to the tests, you'll see they have alternatives such as you have the silver, right? The silver chloride, the silver nitrate instead of the lead nitrate, or the barium sulfate or the barium chloride instead of the lead version of it. So it's better to put these answers than put lead in it. It's better to use that than to use lead.
Thank you.
All right, no problem. So it's better to use that than lead. Okay, so we have gone over the notes, but right now I think we should do some questions. Again, this is a very strong topic, which is why I'm starting with it. I would usually start with that, but I will start with qualitative analysis right now. Okay. Okay. Let me just connect my iPad so I can go about doing this. Again, if you all want the presentations, please send me an email. Please let me know. And if you feel that any of your other friends should be in this, I don't know if you have other friends in the exam too, please feel free to share the link with them. I don't have any problem with that. So that would be very good. Okay, I have the PDF. Let me just send it over. So we're gonna do some questions on qualitative analysis based on the information that we have utilized so far. Okay, based on the information that we have utilized, we are going to do that. Okay, what's up now? Okay. Okay, so we are back with the stuff we're doing. Okay, so we're gonna look at some questions with qualitative analysis. These are all CXC paper questions that I have taken, I have screenshotted, and we're going to do them together. Okay. So it says that a student carried out, let me get a little bit more to see. A student carried out the following test on a pale blue solution of compound X, okay? Complete table 3 by filling in the expected observations. So table 3, of course, would perform on compound X, right? So it says that aqueous sodium hydroxide was dropped, well, added dropwise and then in excess. So the inference is that Fe2 plus ions are present. So that is our inference. So some cases they'll give you the observation and they'll ask you to fill in the inference. Other cases they will give you the inference and they ask you to fill in the observations. Now these questions usually account for the last 6, 7 marks, or sometimes 8 marks of the data analysis question. So imagine out of a possible 25, you want to get as close to that as possible. As I mentioned, these are very important questions. Qualitative analysis always features. You want to maximize the number of points you get on those early questions. So we say that the Fe2 plus ions are present. Now the observation that we should have seen after we added sodium hydroxide is a dirty green precipitate, okay? A dirty green precipitate. That is what we should have seen, a dirty green precipitate. And then in excess, we should have continued to see a dirty green precipitate because it is insoluble. Okay, so you'll have gotten 2 marks for writing the same thing twice. So again, it's something that demands a lot, but it's something that is actually very easy to understand. All right, and then part 2 says the resulting mixture from 1, so that means a mixture with iron 2 is left to stand in air. Now, as we mentioned before in the PowerPoint presentation, the iron 3 plus, the iron 2 in the presence of oxygen will oxidize to iron 3 plus, meaning that we should say that the dirty green color turned to a red brown precipitate, okay? To a red brown precipitate upon conductive air, okay? So you get your 2 marks for saying the color change that happened, right? It changed color to a red brown precipitate. So of course that is the iron 3 oxidizing to the iron 2 oxidizing to the iron 3 by this reaction. So this is what is happening in air. That's what's going to happen. And then the next one says that aqueous barium nitrate was added. So whenever you see barium nitrate, right? So remember we said the 2 test for cations would be sodium hydroxide followed by ammonia. And whenever we see something like barium nitrate, have to be talking about an anion we're trying to discover, okay? So the 2 test for cations all around the board are sodium hydroxide and ammonia. And of course, you can separate the aluminum and the lead based on what we talked about. And for the barium nitrates and these tests, these are for anions. So we're looking for an anion. So obviously in this question, it will want us to determine what compound X is, okay? So it says aqueous barium nitrate was added, right? Followed by dilute nitric acid. So it's saying that we have confirmed the presence of sulfate ions, so SO4 ions in the compound. So therefore, the formula of compound X, the identity of compound X would be, recalling it, iron 2 sulfate, so FeS4. So based on the test we have for sulfate, right, we have that the barium nitrate is going to have the same reaction as with the barium chloride, so don't be afraid, and it's going to form a white precipitate, right? So forms white precipitate. And white precipitate remains. Now, all of this we're talking about, you can find in your textbook, right at the end of your textbook. So everything is there if you want to go over. If you're checking like, boys, sir, I don't know what that is now. I don't think I can do that, okay? So you get 2 marks for saying form a white precipitate remains, and that would be the end. So imagine you're getting 6 marks by repeating the same thing. You repeat one thing the first time twice, another thing again twice, and another thing again twice. That would be the easiest 6 marks you get in your life. You just have to know what you're doing, that's all. Okay? That's the first question. So we're seeing qualitative analysis is not so difficult, but let's look at this one, right? So it says complete table 2 to show the observations and inferences from tests carried out on a solution M. M, okay. So this M is called M, compound M, okay? So it says to a portion of M, add aqueous sodium hydroxide until in excess. So we're adding sodium hydroxide again, it means that we want to look for the cation or the metal ion, okay? And this is where our friend ZAP comes into play. I keep telling you all, watch out for ZAP, because ZAP will zap you like a zapper for real. So inference tells us aluminum or lead or zinc or calcium possibly present. So we have our threesome, well, our foursome in there. And then the second inference tells us that for excess, of course, so the second inference would tell us for excess. Okay, so this shows that the second one refers to excess. That aluminum, lead, and zinc possibly present. Now the only one that is out is calcium. And we know that for the second test in excess, calcium remains insoluble in NaOH, okay? We are aware of that. It remains soluble in NaOH. Therefore, for our first test, we will see that a white precipitate forms. A white precipitate forms. And we see that it is soluble in excess. Okay? So mainly based on the information we have. A white precipitate forms and it is soluble in excess. So that is how we eliminate calcium from the from this set of questions that we have. So do you understand so far how we're applying the analysis to what we're doing? Do we understand so far?
Yes, sir.
Yes, sir.
Right. So what we need to do is apply the knowledge we have already. We need to use that, and I will send the slides. So you actually send it in the chat. I think the chat I have an option to send documents and stuff like that for you. So you will send the slides, okay? Right. So we look at that. So it's soluble in excess. So therefore we're left with aluminum, lead, and zinc. All right. Now, all that is nice and airy. So we go to the second test. So a second portion of M, we said that aqueous ammonia is added until in excess. So the wet precipitate is formed and the precipitate is soluble in excess ammonia. Okay. So a wet precipitate is formed. Now, based on the information that we have, between the three of them that make up our ZAP, the only one that does not, I not say does not, but a wet precipitate is still formed. So therefore, we'll still have to say, I jump in ahead of myself, that aluminum, lead, or zinc still possibly present because they still all will form a white precipitate. But now we add in ammonia in excess being the second step, right? And it's saying that the precipitate is soluble in excess of aqueous ammonia. Now, based on the information that we have, the only precipitate that is soluble in excess ammonia is zinc, right? If it was aluminum and lead, we would have to continue going on our merry way. But because they say that it is soluble, zinc is the only one that is soluble. Therefore, zinc 2+ is the ion present within that. So we have confirmed the zinc. So now we're going to test for our halides. I'd imagine. Yes, testing for our halides. So it said to a filled portion of M, add aqueous sodium iodide. A yellow precipitate is formed. And under here it says ionic equation required. Now, wait. Add sodium iodide. What do you mean with sodium iodide? You might ask yourself that question. But one reaction we can observe with sodium iodide is iodide solution only becomes yellow, right? This yellow will only happen if iodine is displaced. Now the question is displaced by what? Displaced by another group 7 or displaced by another halogen. Because remember, based on that, halogens, they displace each other based on their position, right? So when you're at the top, you can displace anything. When you're at the bottom, you get displaced by the one above you, and so on and so forth. So in this reaction, the yellow precipitate forms because iodine is displaced out of the solution of the compound. So that is what's happening here, okay? So iodide will remain. So the sodium will go to Dweebe with whatever else that was in the solution. And iodine will be left by its merry self. So let's assume that, let's call the halide, let's say, let the halide be X, okay? Let the halide be X, right? So you say that it will either have to be, no, we cannot test for fluorine. So, and we haven't talked about fluorine, so you don't have to put fluorine in your answer. It's either chlorine or bromine, okay? Either chlorine or bromine. And you would put that the ionic equation here would be that you will have essentially, well, I write the full equation before the ionic equation. I write the full equation before the ionic equation. Oh, what's going on? I think my stuff stopped. Okay. So the full equation we would have is the sodium iodide, NaI, plus, let's say, whatever compound contains X, so X minus, to give us NaX plus I minus. Now, based on what you remember from writing ionic equations, you're going to remove all the spectator ions. Now, the thing about this equation, you don't have any spectator ions because all ions actually involved in this equation, really. Iodine would be the spectator ion because it's I plus. But if I were you, I'd probably write everything. Or you could just go ahead and you could just write Na plus X minus to give NaX. So either one looks fine. So you could just write what I underlined here, or you can write the entire equation. So you would put that right over here, and that would be the answer. So you get 1 mark for stating either chlorine or bromine, the other mark for the ionic equation. And then the next one, it says that, so a fourth portion of M, so of course, when you do chemistry, so I'm going to test the same thing over and over and over again. We're going to take a little bit of that, take a little bit of that, take a little bit of that. So the fourth portion of M, add aqueous silver nitrate, followed by aqueous ammonia. So now we get into the test. We're talking about the mirror test, okay? And no observable change given for any of the reactions. No observable change. Now that's funny, yeah? Now, we established that iodine is displaced, yes. But it says that no observable change. Now, what does that mean? What does that mean? Because silver chloride or rather, let's look what they say about M, right? I'm telling you already, it has to be a soluble salt. Because chlorine and bromine have to be present involved in that somewhere. So we add aqueous silver followed by aqueous ammonia. So between chlorine and bromine, we have chlorine that is soluble in aqueous ammonia, and we have bromine that is partially soluble. So therefore, I dare say the answer here is that Cl minus is present. I dare say that silver is present. The reason I'm saying that, I'm sorry, that chlorine is present, and therefore we would have zinc chloride as the answer. The reason I'm saying that is because there's no observable change involved in that, which means that the solution form, you have the yellow precipitate, but the solution itself would be colorless because they're just saying your yellow precipitate form, right? So the rest of the solution must be colorless, and there's no observable change. So I am saying that chlorine minus would have to be present because of that fact. So this one is a little tricky one at the end because you'll be wondering what is sodium iodide doing in this situation here. They want you to realize that this is a displacement reaction occurring between a group 7 elements. And the reason why you have a yellow precipitate formed is because you will have iodine being displaced from the sodium. Iodine being displaced from the sodium. That's what you have happening between the two of them. Iodine being displaced, being reduced, which causes the color to essentially be that. Oh, I made a mistake. Don't make that mistake like me. Remember that group 7 elements exist diatomically. So yeah, remember they exist diatomically. So don't make that mistake I made there. All right. So that is another completion we have. So we had one where we dealt with purely a very easy one with iron sulfate. We dealt with another one when we had to, I think by far the hardest one so far. And let's continue going on to look at some other elements. Would somebody in our class like to attempt this one for us, please? So the question says, in another experiment, the group of students was given another unknown solid B and asked to identify it. They performed a series of tests and made some observations which are recorded in table 2. Complete table 2 by inserting the appropriate inferences. So this time we just doing inferences alone, okay? And this one was 8 marks. So an 8 mark in total, 2016. Okay, so would somebody like to walk us through this one?
Red brownish gas. I would say like bromine is present.
Bromine, right? So a red brownish gas, right? So yes, I agree with you, bromine. So the other thing we didn't talk about, as I mentioned before, we can use the other observable characteristics, right? Between the stuff. So we don't actually have to do the test. There's some things that are just characteristic about them. So bromine gas is evolved, and therefore we have bromine minus. Okay. All right, so that's good. So you can continue first.
Um, the white precipitate, I'll say zap for
So you
number
think,
3.
so you think we have a zap situation here?
Yeah, I think so.
Okay, let's see. So it is of the remainder of B. So the reason why it's in the remainder of B is just preparation step. So we can skip 2 altogether. And when you're reading CSEC questions, it's important to eliminate outlying information that's really not necessary to you. So this, you can just pass this, like, because it doesn't do anything for you. Let's leave a lot of unnecessary information. So as he said, the first portion of filtrate will add sodium hydroxide solution until in excess. So for the white precipitate formed, we see a white precipitate formed. And I agree with him. We're in another zap situation here, because since we form a white precipitate, it could be zinc, it could be aluminum, it could be lead, it could be calcium, right? Right. So white precipitate form, right? So we're gonna put all these as possible options that we have here. And then it's soluble in excess. Now, out of these, he said calcium, right? And these are soluble in excess, right? Now, calcium, we can cross calcium out. Calcium can be eliminated because calcium is insoluble in excess, right? So calcium is out of that. So we are left with zap. So good idea for sorting that out, okay? All right. So that's what we have. So that's another 2 marks, okay, for that question. Okay. So you can continue with the next part.
I'll say the testing for cation, so I'll say the white precipitate is the zinc, aluminum, lead, and calcium, and the insoluble is calcium.
Well, remember we eliminated calcium based on the fact that it's soluble. So it will be calcium. So between the 3 of them, which one you think? Zinc, aluminum, and lead.
Insoluble.
Right. Because all of them again will form the white precipitate. So which one you think we have now? I mean, look at the next part of the question. That should probably give you an idea of what to expect.
Potassium iodide, I'll say.
Right. So potassium iodide is the next step that we have. Now, what 2 cations do we use potassium iodide to distinguish between?
Aluminum or lead?
Right, so aluminum and lead. So
Yeah.
we're crossing out zinc here and making aluminum and lead. So that's good. We're making some strides. So it says, so the third portion of the filtrate add aqueous potassium iodide, right? So it's also a good, as I mentioned, that's why reading the paper before is a good tactic to use in doing the exam. because you kind of see where it's leading to, okay? You can kind of beat the exam in that way by seeing what is required. So it says a yellow precipitate is formed. So based on that, which of the ions we have, which of them would form a yellow precipitate?
Lead.
Right, so lead would form the precipitate because of that we are forming lead 2 chloride, right? So it shows the presence of lead 2 chloride. And we can go ahead and write the reaction for that. The ionic equation, literally we can just put this plus 2Cl to form, and this is insoluble, so it has an S by it. That would be your free max, right? So aqueous is minus, yes. So that would be a free mark. So 1 mark for saying that lead is present because the formation of lead chloride, and then you go ahead to show the equation for forming lead chloride. So this was a nice question. It was a sub question. It was a really fun question to see here. So I think we're getting past we're getting to the place where you need to get to qualitative analysis. As I mentioned, they're not hard questions. They are just questions you need to know exactly what you have to do. And that is why I want to spend more time with it today. Because many times we kind of rush that topic. Many times you don't get to do too many questions with that topic. And many times we sometimes we see the questions and we don't know what to do. But I'm trying to give us some practice with that. That is a very, very important topic for us to finalize. All right. So thank you. I think it was Dimitri. Yeah, thank you, Dimitri. Okay. Okay. Surprised my students haven't joined yet. That's crazy. Anyway, so we have another question. A student carried out a number of tests on a solid mixture labeled Q. Now, solid is a very important step there because it's a new solid. It's not ionic yet. It's not a solution with a solid mixture. So some of the observations and inferences are recorded in table 2. Complete the table by inserting the inferences observations as necessary. So it says that Q is heated strongly in a boiling tube. Brown fumes are seen around the mouth of the boiling tube. Now, brown fumes, that's heat, okay? That's just on heat. So this is where we have to be careful because always saying we heat. Now, the only thing, I forgot to include in this slide, but in your textbook, the only thing that will cause a brown fume there is when you have nitrate is present, right? The reason why, because under heat, the nitrate ion will thermally decompose to give you the nitrogen dioxide, which is that dark gas, and oxygen. So that is where you get it from. And the equation for here is that you will form nitrogen dioxide and oxygen. And this is the thermal decomposition reaction, right? So this is what happens in case they ever ask for the equation. And as this is a solid, that's why I thought it's very important to mention that it is a solid. Okay, so ensure we have that taken down. Plus O2 gas. So it's going to decompose to give you the oxide, the nitrogen dioxide, and the oxygen gas. That's decomposition. Now, because it decomposes in that way, we can already start thinking about what type of charge is on the cation. I don't think it asks for the cation here, but I could already assume which cation it would be. It would have to be most likely a group 2 cation because of that decomposition we have in here. because of the oxide it's going to form. So we would say now that based on that information that NO3 minus is present, but because I see the saying a glowing splint is like rekindled, I will not put the assumption about the NO3 present yet. I mean, we know underlying that's what it means, but I think what they want us to say is nitrogen dioxide is given off. That's what they're interested in for that answer, based on how they phrase the question. Okay, but overall, we know it's nitrogen dioxide that's going to be the same. Next part says that the glowing splint is rekindled. Therefore, we know the only thing that tests for glowing splint has to be oxygen. So oxygen is present, right? And the gases involved are bubbled into aqueous calcium hydroxide, that being lime water, okay? That being lime water. So let's not forget that's lime water. And a white precipitate is formed, meaning that here we have carbon dioxide. Now, it doesn't mean we have carbon dioxide in the thing, okay? It just means that because carbon dioxide is in the atmosphere, that carbon dioxide would react with that as a mixture of gases. So carbonate is necessarily in that mix, but it tells us that because it's in the air, it enters its solution, and that's where we get that carbon dioxide. Okay. Would somebody else like to do the rest of the question? Anybody? Okay. Well, if no one wants to attempt it, let's go ahead. So it tells us now that dilute HCl hydrochloric acid is added in excess to Q and the mixture warm. So the resulting solution, aqueous sodium hydroxide, is added until in excess. A green precipitate is formed, which is insoluble in excess sodium hydroxide. Now we put HCl in that just because it was a solid solution. So to get it into the aqueous state, we just dissolved it in acid. So that's why the HCl is there to dissolve it. But what's important is the sodium hydroxide we're adding until excess. So that's what we're going to focus on, the sodium hydroxide. Okay, focus on sodium hydroxide now. So a green precipitate is formed, which is insoluble in excess sodium hydroxide. Therefore, we're dealing with iron 2. We got that out because it's a green precipitate. Iron 2, a green precipitate. And the ionic equation required is the iron plus the hydroxide ion to give you iron 2. So that's 2. Iron 2 hydroxide. That's the equation we are interested in. And of course, you put your states, aqueous, and solid. So then it says dilute nitric acid followed by a few drops of silver nitrate solution was added to Q, the test tube was left standing in light. So anytime you start seeing silver nitrate and light, know it has to do with a group 7 elements. Know it has to do with your halide elements. Okay? That's the only reason why they'll give you such that information. So once you see silver nitrate, know that silver nitrate is the characteristic test for that. So it says that it was added to Q. Okay. Chlorine ions present. So what they did again, they gave us the reverse. They're telling you, okay, Buster, you know that chlorine ions are present, okay? So we have already established that. Now you're gonna fill in those 3 steps for me and tell me how you know that. So you're gonna fill in the observations. So if we go back to the slide to try to give you access to in the chat, you will see what happened to silver nitrate here, right? And then ammonium hydroxide was then added to the resulting mixture. By ammonium hydroxide, again, CXC trying to make it into a wizard. Because ammonium hydroxide, which you remember, dissociates to form ammonia, aqueous ammonia that bait, which means, in other words, you're just adding NH3. So it's essentially what we've been doing. And I'm going to share my screen again so we can see the tricks. Because CXC loves to trick children. They love to trick children. They'll make your head spin one of it. If it's chlorine, that's what we see. If it's bromine, that's what we see. If it's iodine, it's yellow all the way around. We know it's chlorine. So we're gonna talk about white, right? Okay. So I'm gonna go back to this side. Please, stop. CXC loves to trick children. So the first step would say that a white precipitate forms. We just saw that. A white precipitate forms. CXC. And then leaving it in light standing for minutes, we would say that it turns purple to gray. So that's 2 marks. And then adding ammonium hydroxide, right? Adding ammonia, right? It precipitates, dissolves, forming a colorless solution. And all that you can get based on chlorine. So that is why it is important to know the tests that you are employing in the tests that you are employing in the qualitative analysis. It is important to know the tests that you are employing in this example here. Okay. So that's another question done. And then another one again. This one is very short, which you don't usually see. Okay. The table shows test performance substance label Q and the observations of the test. Complete the table by inserting the appropriate inferences. So it says that a small amount of solid Q was placed in a test tube and heated over a Bunsen burner. A brown gas was produced. Again, it's heat. Again, it's a solid. Again, it's nitrogen dioxide, meaning that it shows the presence of the nitrate ion. So we have that sorted out already. But we cannot be too quick to jump to conclusions because it says that it changes damp blue litmus paper red. That means it's an acidic gas. And if I remember chemistry well, I know that under rain and under acid rain, that nitrogen dioxide with water will react to form nitric acid, which therefore means our answer is correct. All right. No free present. Okay. So that's one. So you get the max for saying that. I just see something in the chat. Yes, thank you, Dimitri. Now I saw it. Acidic. Very great. So a solution of potassium iodide was an intersection of Q. A bright yellow precipitate was formed. So again, potassium iodide. Now we're not sure in what context we're talking about, because we could be referring to a cation here, which most likely means that, because I doubt we'll have another anion involved in this species. But a bright yellow precipitate is formed, all right? Now it wouldn't be iodine, because iodine forms a pale yellow precipitate. So it's not anything to do with non-metals. But because we're adding potassium iodide, it therefore means that lead will have to be present, because it's a bright yellow precipitate on anything of potassium iodide. So that's what we see. And the reaction we have now between the potassium iodide again is to form the ion equation they want is to form the lead iodide, the lead 2 iodide. So we would say that Pb 2 plus I minus 2I minus to give Pb I2. And that's aqueous, and solid. Therefore, the compound Q would be lead nitrate, which is a dangerous compound, as we established before. So this both the cation and the anion present. So we have how many more questions? I have three more qualitative questions, and then we take another break. All right. So students conduct a number of tests on a solution of compound Y. Some of the observations and the inferences made from these tests are recorded in table 2. Complete table 2 by writing in the observations and inferences numbers 1 to 5. Okay, so this time they give you exactly what you want to see. It's 8 marks again. Most of them are 8 marks, as I said. So it says aqueous sodium hydroxide is added gradually until in excess. A red-brown precipitate insoluble in excess sodium hydroxide is formed. Important as excess red-brown precipitate we're talking about here, right? Now, because it's sodium hydroxide, it's a test for a cation, therefore iron is present. All right, be specific, Dimitri. It's iron 3 that is present, okay? So iron 3 is present. Okay. And then number 2 says a strip of magnesium ribbon is added. Now I don't go much further because we should already start wondering about magnesium ribbon being added. Because it's, rings a bell somewhere. But anyway, let's continue. So a magnesium strip is iron, and the magnesium reduces solution. Why? Iron, 2 ions are produced. Aqueous sodium hydroxide is added to the mixture until in excess. A green gelatinous precipitate insoluble in excess sodium hydroxide is formed. Now, in my mind, that sounds a lot like a sulfate. And the reason why I'm saying sulfate is because the main fact is the magnesium reduces solution. Why? Which is what we're dealing with now. And on the magnesium ribbon, right, we're going to have gas being released. So I honestly am certain that sulfur dioxide is being produced there. So it will have to be sulfate, okay? So it will have to be sulfate, okay? Now I have to break it down into 2 points. Like I'm doing the same time as you guys. So I can give you the answer for that. I need to actually break it down to write it down in the proper place. But on the magnesium strip, that's what's going to actually happen. These are the tests we usually include. But again, they're asking you to link information we know to the unknown, that being with the qualitative part of chemistry. So some of these questions are pretty straightforward. Some of them also are very different, but that's what happens with adding this strip of magnesium ribbon, right? So I will say that SO4 2 minus is present. And the iron, 2 ions are produced, right? So what we have now forming is FeSO4. This and that. So what is present? So it's that, oh, sorry, I put that in red, right? So a gas is released. So colorless gas is released because sulfur dioxide will be colorless. Gas is sulfur dioxide. So SO2 is so like I say SO2. So gas is given off. And solution changes color from red brown to green. What happened to? Okay, so that's that. Then freezer dilute nitric acid is added followed by a barium nitrate solution. No precipitate is formed. So dilute nitric acid added by barium nitrate solution. So the method we're adding nitric acid and barium nitrate, I know that this is a test for a non-metal, of course. And because they have no precipitate being formed, I can start ruling out other ones. So for carbonate, we have a precipitate being formed. For sulfite, we have a precipitate being formed. For sulfate, we have a white precipitate being formed. So no precipitate is formed, right? So therefore, based on what we know, we can cross out that no CO3 2 minus, no sulfates, or no, right? And because we have crossed out all the other what they call it, all the other possibilities, we are left with the halogens, right? So the halides are the only option left. So that's why we do the silver nitrate test followed by aqueous ammonia. So here we are doing the silver nitrate test followed by aqueous ammonia testing for these. Now, because again, these chlorine ions are present, therefore, our test, we would say, therefore, that a white precipitate forms, and therefore dissolves when NH3 is added. So that is why these are most times in question 1, because they take analysis themselves. Okay, so we have 2 more to do. So let's just run through those. So complete table 2 by writing the observations for the test carried out on salt S. So a sample of salt S is heated strongly in a dry test tube, very important, it's dry. Moist red and blue litmus paper is held at the mouth end of the test tube. An acidic gas is produced. Nitrate ions are present. So because nitrate ions are present, therefore we know that it'll have to be nitrogen dioxide gas that is being produced. So because of the litmus paper, we know that the red litmus paper does not change color. The blue changes to red. And yes, the blue changes to red. Okay. All right. So blue changes to red. And then now it's saying that to an aqueous solution of salt S, aqueous sodium hydroxide is added gradually until it's in excess, right? And the inference we have is that zinc is present. So because zinc is present, we have another ZAP situation here. Now, the thing that differentiates zinc from the other two is that zinc is soluble in excess sodium hydroxide, right? So we're gonna say that a white precipitate is formed, right? A white precipitate is formed. But zinc, so a white precipitate is formed and soluble in excess to form colorless solution. Okay. All right. And the last one we have for this topic, a student conducts a number of tests on an aqueous solution of compound X. Some of the inferences and observations are recorded in table 2. Complete table 2 by filling in the missing observations and inferences. So to 1 milliliter of a solution X, that's really not important, a few copper turnings followed by concentrated sulfuric acid. So it gets us to start thinking copper turnings, and sulfuric acid. Okay, fair enough, we are the acid. So brown gas evolves, which turns more blue litmus red. We keep going on to the same thing over and over and over again. We have to know that it has to be nitrogen dioxide again. That means nitrate is present, right? Now, is present, right? And then it says to a milliliter of solution X, nitric acid followed by aqueous silver nitrate. Aqueous ammonia is then added until in excess. Iodine ions present, iodine ions confirmed. Therefore, we expect it to be yellow, okay? So pale yellow precipitate forms, and it remains yellow. Okay, because it's insoluble. And now it's saying to 1 milliliter of solution X added lead nitrate. So as I mentioned before, you saw that net before, but it's the same result you'll get with barium nitrate or barium chloride, and a bright yellow precipitate forms. Okay, so a bright yellow precipitate forms. It's not anything different. You're just going to confirm again that it is chlorine. I'm sorry, iodine minus. It's gonna confirm that it's iodine minus that is here again. Okay. But this time it's just to write the equation. So. Okay, sorry. Okay, and with that, people, that is the end for qualitative analysis. We have gone over information. We have gone over the, what they call it, questions for that. Do you have any questions whatsoever on this topic? Do we have any questions?
Yes, sir.
All right. So that is the end of our second session today. And it was one I really had to do because of the nature of the topic. But these are the questions that have been shown for CXC so far. I hope you got some good practice with them. Some of them made us think, some of them were pretty easy. And that's what you usually will get for this. So here's what we have to do, right? As I mentioned, we are going in order of difficulty, in order of frequency. So we have gone through that. Now, when we come back, what I'd like us to do some focus on is do some questions we usually get in A, right? So some of those data analysis questions. So we will do some rates questions. We'll do titration questions. We will do some 0-1 electrolysis questions. Another thing we have to go over is the reactivity series. So we'll try to see how much we can cover. We have some past papers we'll do some book with. But that's what we'll do when we come back. So I will give you all a 15-minute break. So you all can, do what you have to do, and then we return.